Okay, let me start now. So I was trying to do this theorem 3.12. So I'll try and show the proof of this. So the idea is that you have a function x from a sample space to another place t, and then x generates a probability q on t given by this formula. Q of b is equal to probability of x inverse of b, and I have to show that this q indeed is a probability. So one assumption I always make in this whole this whole section or chapter is that I'll always assume S to be either finite or countable. Okay, so in that sense, I'll restrict my space. So number of outcomes in a sample space are discrete. So now the idea is that I have to show that this is a probability. Okay, let me try and do the proof of this. So what all do I have to show? I have to show first that in this, if I want to show a proof of this, I have to show first that the two axioms are probability. Right? So what is the proof? The proof is, let me go here, change the color a little bit, keep maroon, I have to go a little bit more. Very good. So here the proof is the following. What is the proof? In the proof, I have to show what? I have to show two things. I have to show Q is a probability, right? So Q is on, so Q, T is a sample space, and I have the events are all power sets, subsets of T. Events are all subsets of T. I take that. And I have Q of B, any event B, which let's call this as F. I'll go back to black. So B and F, Q of B is equal to, I define it as a probability of X inverse of the set. Very good. That's very good. So now I have to show Q is a probability. So the first thing I have to do is I have to first show, so what is X? X is a function from S to T. And P is a probability of S. This I'm given. This I'm given. This is given to us. So now what I have to show? The first axiom of probability I have to verify is I have to verify two things. So I verified the two axioms of probability. Okay. So what are the two axioms? The first axiom is I have to show Q of T is equal to 1. Right? So how do I verify that? So what is Q of T? So let's verify that. Let's write down maybe in blue. So that is how to verify that. So Q of T is what? Q of T is probability that of X inverse of T. But X is a function from S to T. So everybody in T has to fall in S. So same as probability of S. And that's equal to 1. Okay. Because X inverse of T is the set of all S in S such that X of S is equal to T. But X is a function from S to T, so this has to be equal to S. Right? So that's equal to C. Because. Now, the second thing you have to verify is a little bit tricky, but once you know the set theoretic ideas, it should be easy, right? So what do you have to do? You have to take B1, B2, Bn, and so on and so forth, be a sequence of disjoint events, right? In T, right? And what do you have to show? You have to show Q of the countable union of I equal to 1 to infinity of the BIs is equal to the sum of I equal to 1 to infinity of the Q of BIs. Right? This is what you have to show. Right? You have to verify this axiom. Right? So maybe here I'll write it as this is a different one, maybe a different color. And the Y is again color. So this proof of this plane is proof of 1 is here. Similarly, let me write down the proof of 2. So what does proof of 2 give you? How do you show this? So again, let's look at left hand side. So Q of the union I equal to 1 to infinity of the BIs, right? What's that going to be? That's the same as the chance probability of x inverse of the union I equal to 1 to infinity of the bi's. Now what is that? Now this you have to be a little careful. How do you do this now? So you look at x inverse union I equal to 1 to infinity of bi's, right? So the little exercise, which I won't show, it's a small exercise. One can show that this is the same as union I equal to 1 to infinity of x inverse of bi. So given that Bn, this is just definition. So this is a set theoretic exercise. Right? So once you have this, you're in shape because now you go down, you say, okay, fine, this is the same as, this is the first claim. So the first claim, so this is claim one. Let's start claim. This is the star. Let me call it a star. Star here. Then the next one is you have to go. So what do you do? That means from star using star. So using star, I get Q of the union of I equal to 1 to infinity of bi's is the same as the probability of union I equal to 1 to infinity x inverse of bi. And that's the next step. That's it. Now the next claim is the following that you have to do, let me call this double star claim. Right? This only you have to verify again. I'll leave it exercise. bi I equal to 1 to infinity are disjoint and x is a function will actually imply, so I'll just give an exercise again, you can check about that x inverse of bi are also disjoint. Are also disjoint. Or disjoint events in S. So x and b are disjoint events in P, and x is a function will imply that x inverse bi are also disjoint events in S. So once you have this, since P is a, so again, since P is a probability on S, probability on S, so what do you get? You immediately are on your way. So it implies Q of the union I equal to 1 to infinity bi. Here I use double star. No, not here. The same as is the same as the probability of the union I equal to 1 to infinity x inverse of bi. I already know this. Now, since P is an axiom of 2 and axiom 2 of probability, and double star will imply the same as probability I equal to infinity probability of x inverse of bi. Because x inverse of bi are disjoint events in S. And that's the same as sum I equal to 1 to infinity q of bi. So I verified the two axioms of probability. One is q of s is 1, and the other one is that q is countably additive function. That means these two things will imply that q is a probability. So these random variables will sort of go across and give you functions in the other spaces. So it's an important result. I won't. I think it's simple to show, but one must keep track. So one can shift functions across sample spaces, and the probabilities go across as well. So it's an interesting sort of idea. These define a certain concept. So let me write the definition down. Uh, okay, the definition down. So definition 3.1.5. Right? So here, what we will do is the following. We will say a discrete random variable is, so this is the definition, random variable is a function x from S to T, where S is a sample space equipped with probability T, with a probability P, and T is a countable space. So always my S is countable, okay? T is countable. And T is a countable or finite subset of real numbers. So I'll only look at random variables that go into real numbers. These are called discrete random variables. And we already know that X will distribute probabilities across T by the function Q from the previous theorem. But what we'll do is we'll define a function f sub x from the T to 0, 1, T to 0, 1, given by f sub x of T is the chance that X is equal to T. Okay. And so then define f sub x is equal. Then f sub x is called the probability mass function. Mass function of x. Then what you can do is you can do several things. You can do with this little f and capital X. So there's two notations I've introduced. So the notation is the following. So if you want to count chance of x is in A, then x is in A, that's the same as, you could think of it as the sum over T in A, for which probability x is equal to T, because that's how you can use the axiom of probability of P to do this. Or you can think of it as the sum over T in A, f sub x of T. So you can use the function f sub x to do this. So A is an event in T. So A is subset of T. Then for A in subset of T, let me erase this little bit so that now properly. Then for A in subset of T, this. So you can use f sub x to do that. So these are two aspects of random variable that we use again and again. We'll identify the probability mass function and then get the answer. That's one aspect of random variables. Right? So let me do a simple example. Let's go to a simple example. Let's say, so again, when you describe random variable, we only want to describe, we don't worry about the sample space. We only worry about what values random variable takes. So that tells you exactly everything about random variable. Okay. So, so let me do an example. Let's say we'll say X is a uniform. I'll just say X is a, let's say, Bernoulli P if the following happens. So there is some sample space S from which X is from S to 0, 1. Okay. And what you'll do is, the sample spaces you don't worry about, and P is a probability on S. On S, and then the chance that X is equal to 0 is going to be equal to 1 minus p, and the chance that x equal to 1 is going to be equal to 1 is going to be. This is what I would call my Bernoulli random variable. So we'll say x is this if there is something sample space s to 0, 1, p is some probability on s, but the distribution of x is given by this. So that you could write in short form that fx at 0 is 1 minus p, or in other words, fx at 1 is just p. So the distribution of x is specified by the range it takes and the probabilities of how it distributes it on the range. That's called the distribution of x. And then we discuss. So let me do one. So how do you compare two random variables? Let me just discuss that a little bit. Stop. So now here's the definition. 3.1.6. Let x be a function from s to t, right? And y also be a function from s to t. So you have two functions from s to t, and they are both discrete random variables. We say x and y have equal distribution provided the following happens. That is, provided they distribute the probabilities the same way. Probability of x equal to t is the same as probability of y t for all t. So the probabilities are the same. You say x and y have the same distribution. I should just repeat this. Equal distribution, not distributed. Sometimes you use the same equal. Sometimes you use the word same. So they all mean the same thing. So that means you identify every random variable with the distribution it provides on the real line. Right. So now let me just list out some common distributions. So let's list out some common distributions. So here's a definition. So I'll define random variables of this form. 3.7. So I'll define two things we've already seen before. So I'll say x is uniform 1 up to n for some n bigger than or equal to 1 if the following happens. If x is a random variable, x is a discrete random variable, such that the probability of x equal to k is the same as 1 over n for all k less than or equal to 1. And we say x is a uniform random on the set 1 up to. So just notice I've really not worried about what s is, what the events are, what p is. All I'm concerned is how x distributes its values, how x distributes the probabilities on its range. That's the only thing I'm worried about. Okay, that signifies everything I want to know about x. So let's call this A. We'll even move the dot. So then let me do B, let me do another one B, which we already seen also, like I discussed before. I'll write it properly now. X, I'll say X is Bernoulli. I'll say X is Bernoulli P for some P between 0 and 1 if the following happens. If X again is a discrete random variable, such that the probability of X equal to 0 is 1 minus P, and the probability of X equal to 1 is 1 is P. And we say that let me go down a little bit. That's clear. The two things are clear. So we say X is a Bernoulli random variable. Bernoulli random variable with parameter. So the context. So you should go back and see that I've just forgotten about sample spaces. I've just said, okay, I have a random variable. I specify the probabilities it takes. So with that, the range comes, and how the random variable distributes the probabilities on the range. And that's enough for me to do calculations. I don't worry about S and what S does and so on and so forth. So now we can do the same thing. We can discuss binomial. We can do, let me write all these things down. It's clear to all of us, we're the same page. So I'll write down, I won't write down everything, but I'll write. So I can say X is binomial, NP, if again, we have P between 0 and 1, and N is bigger than or equal to 1. X is a discrete random variable. Such that the chance that X is equal to K is going to be N choose K. Sorry, N choose K, right? In the notation here, in this last note, so I write as N choose K, P power K, 1 minus P to the power N minus K. So that's something you can define as random in this fashion. So now what we want to do is I want to work with random variables. So I have to also understand how other concepts that we discuss about independence and stuff like that go across to random variables. So that we will do next. So let me do this other concept called independent random variables. So this is 3.2.1. So here what happens is the following. So here I have to translate independence from events to random variables. So here's the first definition of the following. Definition 3.2.1. So two random variables X and Y are independent. So there are two functions now. So when do you say they're independent? So what you do is you look at all possible combinations. You look at independent if the following: if X in A, the event X in A, and the event Y in B are independent for every event. So it's very important. For every event A in the range of X, and every event B in the range of Y. Okay, so just the notation here a little hairy here. So X goes from, let's say, X2. So the way you think about this is that X can go from, let's say, S to some T1, Y can go from S to some T2. They all are functional the same sample space, but they're independent if this happens. That is, if X in A and Y in B are independent for everybody in the range of X and everybody in the range of T. Okay. So A is subset of T1 and B is subset of T2. Okay, so just keep in mind that I've sort of moved the notion of independence from events to random variables by getting corresponding events that specify the random variables. So when you do these things, you have to be a little careful. You have to sort of for random variables, you must just check what happens. Right? So you can't do it for. So one simple remark after we'll come back and do this next time, a little bit more in detail, is the following: that so what does this say? That is, you want to say that is so equivalently. Let me do another slide. So equivalently, X and Y are independent if what happens? So the first thing we know is that the chance of X in A, right, this event, and the chance of Y in B, that's the second event, that's the same as the chance of X in A and the chance of X in B for all A subset of T1 and B subset of T2, right? So that's how you define independence. That's how. But what we can do is, we don't have to do this all the time. So we have this tool, we have already seen probabilities are defined by probability of every outcome. So this is an exercise one can show, which I will not show in class, but you can easily check, is that this equivalent to the fact the following kind: X and Y are independent. You don't have to check it for everybody, every event A, if independent, if probability of X equal to T and Y equal to, let's say, S is the same as chance that X equal to T times chance that Y equal to S. It's enough to check for these particular events for all T in T1 and all S in T2. It's enough to check for these specific events. You don't have to check it for everybody. So this we will try and come and make it rigorous next time.